Let's look at type 1 errors, type 2 errors, and the power of the test in hypothesis testing. A type 1 error is rejecting the null hypothesis when, in reality, it is true. A type 2 error is failing to reject the null hypothesis when, in reality, it is false. In practical situations, we will not know for certain if we made the correct decision or if we made one of these two errors. Suppose we test the null hypothesis that mu is equal to 10 against the alternative that it's greater than 10, and we carry out the test in the usual ways, and we end up rejecting the null hypothesis at an alpha level of 0.05. One of two things occurred. The null hypothesis is false, and we rejected it, so we made the correct decision. Or the null hypothesis is true, and we rejected it, so we made a type 1 error. And in practice, if we reject the null hypothesis, we are simply not going to know which one of these two things occurred. But suppose instead that we carry out the same test and we do not reject the null hypothesis at an alpha level of 0.05. Well, here again, one of two things occurred. The null hypothesis is true, and we did not reject it, so we made the correct decision. Or the null hypothesis is false, and we did not reject it, so we made a type 2 error. Here in table form are the possible outcomes of a hypothesis test. In the columns is the underlying reality, and that's going to be unknown to us. In the rows, I have the conclusion from the test, which is going to be known once we carry out our test. If we end up rejecting the null hypothesis, and the null hypothesis is false, we made the correct decision. But if we rejected the null hypothesis, and the null hypothesis is true, we made a type 1 error. If we do not reject the null hypothesis, and in reality the null hypothesis is false, we made a type 2 error. But if we don't reject the null hypothesis, and in reality it's true, we made the correct decision. Some people find it helps to compare the conclusions in a hypothesis test to the results of a criminal trial. In a criminal trial, we test the null hypothesis that the defendant did not commit the crime against the alternative hypothesis that the defendant did commit the crime. In a criminal trial, we give the defendant the benefit of the doubt and use terms like innocent until proven guilty. Well, it's similar in a hypothesis test. We will only reject the null hypothesis if we have very strong evidence against it. In a criminal trial setting, a type 1 error would be convicting a person who, in reality, did not commit the crime. In other words, rejecting the null hypothesis when it is in fact true. A type 2 error is acquitting a person who, in reality, committed the crime. In other words, not rejecting the null hypothesis when it is in fact false. Nobody likes the idea of spending the rest of their life in jail for a crime they did not commit. And so, as a society, we've decided to make the probability of a type 1 error small by using language like beyond a reasonable doubt. The probability of a type 1 error, given the null hypothesis is true, is called the significance level of the test, and it's typically represented by alpha. We get to pick the value of alpha that we feel is appropriate for any given problem. The probability of a type 2 error is represented by beta. The value of beta depends on a number of factors, including the choice of alpha, the sample size, and the true value of the parameter. It depends on other factors as well, such as the alternative hypothesis and the variance. The power of a test is the probability of rejecting the null hypothesis given it is false. Power is 1 minus the probability of a type 2 error, or 1 minus beta. And of course the power depends on the same factors as beta does. Alpha is the probability of a type 1 error given the null hypothesis is true. And we choose the value of alpha. So why not choose alpha to be some tiny value so we're not making a lot of type 1 errors? It is because of the relationship between alpha and beta. If we decrease alpha, then beta will increase. If we choose a very small value of alpha, we will be making it very difficult to reject the null hypothesis. And so type 2 errors will be very common. If we choose a larger value of alpha, it will become easier to reject the null hypothesis, and so type 2 errors will be less common. Let's take a look at the relationship between alpha and beta for a test of the null hypothesis that mu is equal to 0. To calculate beta, I had to make a decision on a few of these quantities down here. And I show how to actually calculate beta in another video. For now, let's not worry too much about my choices there or how to calculate beta, and let's focus on the relationship between alpha and beta. Over here I put in the power, which is simply 1 minus beta. If we chose the common alpha value of 0.05 and we went up here, we'd see that the corresponding beta value is 0.77. That's the actual calculated value. So the probability of a type 2 error in this scenario is 0.77, and the corresponding power of the test is 1 minus that, 0.23. If we let alpha increase from 0.05 to 0.1, then we're going to be decreasing the probability of a type 2 error and increasing the power of the test. If, however, we chose an alpha value that was very near 0, beta would creep up very close to 1, and our test would have almost no power. So there is a balancing act between alpha and beta. But in many practical situations, people simply pick an alpha level they feel is appropriate and let beta fall where it may. Alpha is usually chosen to be a small value, like 0.01 or 0.05. But for completeness, let's look at the relationship between alpha, beta, and power over all possible values of alpha. If we choose a value of alpha very near 0, then depending on the other factors, beta will typically be very close to 1, and the test will have very low power. But if we were to choose a value of alpha over here near 1, beta would be close to 0, and the test would have very high power. But in statistics, we do not like making a lot of type 1 errors, so alpha is typically chosen to be a small value, like 0.01 or 0.05.